Summer student. Today we have the presentations from the summer students. Now we're recording, I say it again. The first one to go is going to be Juan Antonio Molina, who's been suffering under my supervision. So, go ahead.
Okay, so as Alejandro said, my name is Juan Molina, and I have studied supernovas here with Alejandro as supervisor. First, I want to thank you, all of you, for these 2 months because I have learned a lot of science related to supernovas. I have a lot of lunches with CEFCA staff. I have gone to Calzada, so thank you, all of you. And now I start with supernovas, which is the title of classification of supernovas with J-VAR. And first, I want to introduce the topic. Probably all of you know what is a supernova, but I want first to say that supernova comes from stellar nova, that means new stars. And a supernova is a powerful and luminous explosion of a star that happens at the end of their life. And supernovas are a type of transient, and transient is objects in the universe that have variations in luminosity in a small space of time. This is not important, not much important from this presentation, but I want to say it because later we will see that supernova have a lot of types, but it's important that a supernova is a type of transient. And in the photo in the left, we can see some of the transients discovered depending of the brightness and depending of the time on the time. And the transients, the supernovas that we are going to study are in this site. So here I'm showing one of the first supernovas discovered and one of the last that was discovered in CEFCA. So as I said, supernovas have been discovered years ago. And the first that is said to be discovered first is HB9. Other authors said that this was not the first, that was SN185. But this is an interesting story because they said that the ancient people in India put the supernova in a rock, and they put like the picture in the sky and exactly get correlation with the stars, and there are like 2 suns, one with the sun and maybe the other one is the supernova. It's really nice, but the thing that I want to say to you here is that until the last century, the supernovas was described in a qualitative way, as I put here in a book, the book of Baker who compared the supernova with the size of a bamboo mat and said that they have pleasing and otherwise colors, and it's interesting. But now we can study these transients in a quantitative way. And this is mostly done by studying the light curves. That is a plot of the brightness versus time. Depending on the type of supernova, there are different shapes, and depending on the shape, we can study, for example, the progenitor star. And another topic that is useful to study supernovas are also useful to study cosmological distance, because you can get correlations with the standard model or not, depending on the distance and the brightness. And as I said, there are different types of supernova depending on the shape. And here there is a In this figure, we can divide supernovas into mainly two types, thermonuclear and core collapse. The first one, thermonuclear, are just the 1A supernovas that are those ones that happens when a white cloud explodes when they rise the upper limit of Chandrasekhar mass. And in the other side, you have core collapse that occurs when a mass starts explode because it doesn't have enough material to make nuclear fusions. And the main difference is if they have hydrogen lines or not. If they don't have it, we can say that it's a type 1. If they have it, a core collapse. And then here's a little bit tedious because you can classify this type 2 of supernovas in too many ways. If you look at the shape of the core, you can say that it's or a 2P if it has a plate in the light curve, or a 2L if the fall of the brightness is linear. And if you go to emission lines, you can look if they have helium lines or not. And also there are other classifications for the hypernovas that are supernovas with more brightness. But for this presentation, you just have to know what is a 1A and mainly 2P, 2L type. We are going to see also some 2M supernovas. And the principal objective of my project is to see if J-VAR can classify supernovas. And to do this, first I have studied one specific supernova, that is SN23IXF. And then I will take a lot of supernovas to create an algorithm to classify the supernovas using the J-VAR filters. So first, I start, as I said, with one supernova. This one, that is a 2P supernova. Remember that has the day in the light part. And this, I have studied this supernova with two different data. The first one, you see the TX14 telescope in Javalambre, and using the these three Sloan filters. And here we have the light card in the three filters, in the green and in the red one. And we can see the plate of the supernova. And I have fitted this light card using the Basin's function that is here, that has four main parameters. We have A and B that are normalization and constant parameters, and time parameters that are tau that said how long is the rise and the fall of the supernova, and T0 that is related with the time of the peak. In the next slide, we have the fitted. Sorry, I have to say first that we have missed the peak, and it's good that we have a lot of points, but because we missed the peak, some time parameters get negative because they are saying that the time of the peak is in the past. So here we see the fitted parameters in this table, depending on the bands. And I add another one that is M15, that the definition is the difference in magnitude between the peak and 50 days before. And it's a good parameter to classify supernovas also. And here it's important that we see some correlations due to the color variation, because it's very common that a lot of supernovas start with a bluer brightness and then gets redder. So that's why we find some correlations with the bands, with the peak, and with the time of fall and rise. And now I'm gonna explain the same supernova, but instead of fitting with Basin function, I have used SN Cosmo package of Python, and I have fitted for the three filters. And as we can see in the J-VAR is quite good the fit, but we have some problems for the points in the end. But we have some problems in the radar bands, and this we are when it happens in another supernovas that I'm gonna show later. And we don't know exactly why this happened. Also, there are some two peaks that probably is due to the latte, but we are not sure why these uncertainties happen. And we are thinking that maybe we need another fit model for this type of supernovas or of this type of supernovas. And here I show the color variation that I said that the correlation of the parameters with the bands are due to the because the supernova gets redder with the time. So now I'm gonna do the same study of SN23 IXF, but using the J-VAR filters. They are now we have 7 filters, so we have more information. And just say that J-VAR is a photometric survey. They have 7 optical filters and is good enough to study transits, classify them. That is the objective. Here we can see the, the transmission of the filters, the efforts, and the progress of the survey. So to study the supernova with these 7 filters, first I did a cross match between J-VAR and J+, and then using reference star, I plot the pool of growth to see at what aperture has the highest signal to noise ratio to work with aperture for the magnitudes. And then I could correct of offsets because I forgot to say, but J-VAR use non-photometric nights, so it's important to correct this phenomenon. And here we have the full flight of the supernova and the correction. Once is this done, we can plot the light curve in the 7 different filters. In the right, you can see the different panels for the different filters. We can see that the latte, the curve light is more latte for the weather bluer bands and redder bands and we have some problems with this curve light because we have a few points, and we have problems with the converge of the Bayesian function. So we didn't apply it because we have some gaps that give us a lot of problems. Remember that with DX40 we have a lot of points in different times, and now it's very dispersed the points. So then we try to use the same study with SN Cosmos, but we find also problems in the radar bands. It's true that for the bluer bands in the top, we have quite good results, but in the radar bands we have high discrepancies. But I have to say that these discrepancies we are still studying because we think maybe they are because of the 0 points. Maybe we don't have applied well the 0 points to the fit of the light curve. We would have to read more about SN Cosmo packets. But I'm sure that we will solve these uncertainties. So now I'm gonna change the topic a little bit. As I said, the objective is to classify supernovas with J-VAR, and I have studied first one, the one I have explained. But now we want to to extrapolate the study for a lot of supernovas. So we have choose a supernova catalog survey that is called PESTO, Publication Spectroscopic Survey of Transient Objects. And just to say that this catalog uses the NTT telescope with two spectrographs, EPOS C2 and SOFI, and it has a 20 magnitude limit. And the objective of the survey to classify the different transients. So first we do a first analysis to see what kind of transients PESTO has. And we see, because this is in the right scale, that most of the transients in PESTO are supernovas of 1A type, and that this is good for us. But it's important to know that most of them has a low average of number of spectra. With this I mean that a lot of supernovas that are collecting PESTO have maybe one spectra, and one spectra means that we have only 1 point of the light curve, and this is not good for plotting. And this is because
Te faltan 5 minutos.
This is because PESTO just wants to classify the supernovas, and they take one spectra only. With one spectra, you can classify most of them. So here I show a spectra and an example of the table. So here I have also we can plot this. This is the interesting thing of PESTO, that we can plot the spectra versus time. And here are two plots that this one is very interesting because it's like a spectra plane, a light curve plane, because you plot the wavelength versus the flux and add the phase, the time, and you see the tip of the supernova and then the explain. And this is another way to plot it. Be careful that they are different supernovas. This is 1A and this is 2B, and you can see the evolution of the line in the vision lines. So we have select some supernovas that have too many points, and this one was just a few supernovas, because as I said, most of them have only one spectra. And we did synthetic photometry using SM Cosmos packets also. And this is like the equation that SM Cosmos gives to do this synthetic photometry. And using the synthetic photometry to the spectra, we have plotted the light curves. And here are some examples for 1A and 2 type supernovas. In the other side, we have the color variations, and this is very interesting because we see that higher color variations are shown for 2 type supernovas. And at the end, as I said, we want to do to classify supernovas. So to do this, we have used this stretch method that is based on rescale the magnitudes and the times to create an empirical template of the light curve to the different types of supernova. So we have normalized the magnitude to have for the same peak, and the stretch method is based on rescale the time axis, stretching it or not to create the universal template. So first we have fitted some supernovas. This study is made for the 1A type, and we have used the spline methods because we have trained other ones, but this was the best one. Here's an example of using the reference card light of supernova and the science one, the one that we want to apply the stretch method. And this is an example for only one. But if we do this for the 1A supernovas of PESTO, we can see things like this. This is the stretch method applied for the J-VAR. And here we can see some problems. The first is that we have only a few supernovas, like 8, and we thought we should obtain more, but this happens because, as I said, Presto has a lot of supernovas with only one spectra, so we don't have the light curves. And when we did this, we find a problem that these don't work in other filters. Also, in the H alpha filters, we have very strange problems. So we have the conclusion of this is that substellar supernova will need a detailed study, and with this I mean that we need a lot of points before and after the peak, and divide in an equal period of time. And in this way, we could have like a catalog of light curves that will allow us to create templates to classify the supernovas using the 7 filters of J-VAR. And thank you, this is all.
Staying time. Questions, comments?
Yes.
Anyway.
I was wondering, the J-VAR, you have the broadband small filters as for the T40? Yeah. Did you check they were compatible?
Yes, if you plot the light of S23 with the, for example, with the J-band and the 2 different telescopes, you see that the points are the same at the end of the plot, but at the beginning there are some difference. And for example, with the J-bar, you can see like the beginning of the peak, and with the X40, you don't see that peak. So there are discrepancies, and maybe are because of the synthetic photometry, or sorry, the synthetic photometry was not making that, but we have some discrepancies there.
Have you tried combining both data sets to see if an SN Cosmo will work better after the peak points that you were mentioning from J-VAR?
So the
two data sets from T40 and J-VAR, and run SN Cosmo on the combined data set.
Combining data, I didn't try. I have tried the different light cards separately, but no. But it's a good idea.
First of all, thank you for your talk. It was very nice. I have one question. Well, I have 2 questions. The first one is regarding the red bands that you appear to have problems both in the T40 with the basing functions, but also with J-bar and the SN Cosmo. I know you already mentioned that you need to investigate this more, but do you have any idea why this could be happening? Because it seems like the bluer filters are doing more or less fine, and this is just happening in the redder filters, and it seems systematic. So the problem that you see with the basing functions is more or less the same, right? That the one that you have with the SN Cosmo, or because I think both the points are below, right, the expected curve.
Maybe it's true that the model that I have applied is a model of 15 years ago, so maybe it should be redo it. And also maybe it could be because of the ferro points, but I don't know exactly, because it would like another peak that also I don't understand, because the 2P supernovas have updated. So I prefer the basing function, but if you miss the peak, it's difficult to make it convert. And also the basing function gives you more information.
And then regarding when you're creating let's say, the average profile using splines. So splines tend to do wild things when you have very few points. So have you tried any other functions, or some that are physically informed, like
the basing function is the best one, but as I said, there are a lot of supernova don't have the peak, and it's not a good option. I have also tried interpolation, but at the end I choose splines because I think it's right better the shape of the light curve. But also I find some problems with some supernovas because most of the supernovas have one peak and maybe the splines do things like this, and the end. So it's true that when you apply splines, is I prefer the bashing function because it's like the physics one, the more physical function. But we have to choose this at the end because of the data of the police.
Yeah, well, I don't know, but maybe you could simply, once you have your benchmark, let's say the average one, maybe you could just measure the chi-square just with the difference of the points to the curve, specific curve, instead of trying to interpolate with the splines for the individual sources.
Yeah.
But I don't know, it's just something.
Yeah.
Thank you.
Hector, and then Steve.
Two questions. I assume that the supernova we were dealing with was not part of the J-VAR diagram. This is why you need to calibrate the data
Yes.
from the restoration.
Oh.
And the other question is whether you showed that the TX40 data fits when you use that model seems to work quite well. But is there any physical? Can you infer some physical properties of the supernova from the parameters that you fit? I mean, you get some fitting of the time scale and so on. But is there any relationship, known relationship with the physical parameters?
You mean this plot?
Yeah, I mean that when you fit the function, you get quite reasonable values for the parameters, which have to do with the time scale and so on. But is there any? Can you infer from that any physical information of the besides that? I mean,
the main information is that gives you the kind of the fall and the rise. Maybe you can use it to classify supernovas. That is basically like the template with the stretch method. And also the M15 parameter is not from the feed, but it's also another parameter that is quite common in the papers to classify. The main information are the kinds, the fall and the rise. The 2P ones are a more higher times of rise. The 2A have less. You will have means to be but there was some function of the best one to study the physical way of
It seems surprising that you have discrepancy. And I'm leaving, sorry, I'm missing the next one. I know you have to switch. It's just as a comment that the first model seems to fit well. The casing function, right? The previous slide is fitting very well, but then the Cosmo MC is fitting terribly. And you see no evidence of this peak, which seems really, and you're missing light a few days later in all filters. So
with the Basel function is like an universal equation for all types of supernovas. So and this one is you have to have like a prior to know what type of supernova you are fitting. Okay.
thank you.
Antonio, don't take it personally, but we really have to switch.
Okay. Quick question related to what Hector said. I think this Bayesian function, even if it is some empirical parametric thing, it's somehow related to the physics of the supernova, right? This time scale, this tau, should be related to the yield of the different radioactive elements that are produced, and depending on the abundances, they can be different. So, can you say something about the physics?
Yeah, it must be related with the energy of the supernova. That's hence with the mass of the project.
I mainly study the observation of the light particles. In once I don't study a lot of things related to the elements or the physics of the supernova. I just center my study in the observation, but it will be the next step to find why they have some one peak or two peaks because some elements or the stellar medium. But
All right, we really have to switch to the following speaker. Let's step. So the last speaker of this session is Sergio. I keep forgetting the surnames. Thanks, Sergio Turrado, who's been working with Jairo. Jairo, you relax.
Sit down. Yeah.
No, sit down. Relax. Relax. Sergio, te voy a hacer señas 5 minutos y 1 minuto.
Perfecto. Okay, so thank you very much for attending my presentation on the history of the Milky Way through Gaia. I will be presenting the work I have done here in the summer internship under the supervision of Jairo and Andres. So, first of all, of course, I have to present the work that is done in the department I've been part of. So, we are going to study the stellar populations in the Milky Way, and what I want to convince you of today is that by looking at the data, mainly photometric, of several stars in the Milky Way, we can infer properties of the Milky Way past, such as mergers or maybe even dust accretion from the halo. So this is why this kind of work is important. There is a lot of precedent in this field. For example, it's been known for quite some time now that there are two populations in the Milky Way disk. Just as an example, the way we look at it is through spectroscopic data, we measure the alpha elements, iron and hydrogen abundances, and we do this kind of plot in which in the y-axis we have the relative abundance of alpha elements versus iron, and in the x-axis we put the iron versus hydrogen abundance. And when we do this, we see in the density that there are two distinct populations. And this is what's become known as the thin disk population and the thick disk. The thick disk would be alpha enhanced, since it's an older population. There are physical reasons behind that we can infer. This is not the focus of our study. Instead, what we're going to be looking at is a color magnitude diagram. So, as a reminder, in case someone in the audience doesn't remember very well, the color magnitude diagram is a plot in which in the x-axis we plot the difference between two color bands. This is supposed to be a proxy for temperature, as you know from black body radiation models. The lower the object is, the hotter. And in the y-axis, what we plot is the luminosity in a broad band, which is supposed to be a proxy for volumetric luminosity. And if you plot this luminosity versus temperature plot, that's called a Hertzsprung-Russell diagram. In this case, it's a color magnitude diagram, a proxy of that. And what you get when you do that with a lot of photometric data is this sort of Y-shaped, and notably, if you compare the color magnitude diagram with evolutionary theoretical models, you can infer properties, like in this example, the age of the different stellar populations seen here. So, well, in this case, we're only seeing the brighter part of the color magnitude diagram, and you'll see the rest later. So, yeah, the advantage of using this photometric service is that the strength is in the numbers, right? You plot a lot of different data points, and this is less time consuming than doing spectroscopic surveys, for which you also need a lot of photons, and in this case, it is sufficient with less. So that is why we have wider ranges of mass on stellar phase. We have, in general, more data. We are going to be looking at what's called the star formation history, which is basically saying how many stars the galaxy has been forming throughout time, at what rate it's been forming. In our specific case, we're going to restrict ourselves even more we're going to look at the solar vicinity. And what we understand by that is a 100 parsec radius sphere around the sun. And the advantages to restricting our study here are numerous. Mainly, we have very, very good astrometry, so we control very well the parallaxes and we know very precisely what the distances to these stars are. And photometry is also very good because, for instance, there is very few dust in the solar vicinity. This is also very well known. This is also to say that we haven't corrected for dust since we are considering that in the solar vicinity this doesn't affect our study very much. We also know the metallicity and chemical composition, so study is very well. So in order to do this study, we have to compare with what's previously done, right? This is science. And probably the most important paper is Galar 2024, which is pretty recent. And here you can see an example of this star formation history. It will be this plot here, in which you have in the x-axis the age, and in the y-axis the star formation rate in solar masses per gigayear. So you can see that they get this spiky distribution of star formation rate. And here in the right lower panel, you can see the metallicity distribution of the data. And they are getting more or less a normal distribution centered around subsolar metallicity. It is also worth noting that they are using the same dataset that we are going to use and the same isochron, which I will explain later, the same isochrons as we are going to use. So we can compare with this. So as promised, this is the complete color magnitude diagram. This is the region I showed before, and this is the entire one. And you can see this beautiful plot from the Gaia EDR3 early data release 3 catalog of nearby stars, in which most of the stars are here in the main sequence. Then there are several other things. In yellow, you have the excluded data points from our study, and in blue, the selected ones. So mainly what we did is we selected for what's called relative unit weight error less than 1.5, and the points which have RUE near 1 have good photometry, and that's why we are using them. Then what happens with Gaia bands? Gaia has 3 bands. There's a broad band that's called G, and then inside that band there are 2 narrower bands that try to select for color, and these are the red and blue bands. But what happens is these 2 bands their transmission curves don't exactly overlap that of the G band, and you have to also correct for color excess, which we have done. We have excluded voice words, sorry, Alessandro, and we have also excluded, we have restricted ourselves to apparent magnitudes brighter than G19, since fainter stars are not useful for our study. So we are going to try to retrieve information from this dataset using what's called isochron. So what is an isochron? An isochron is a theoretical curve that displays what in the color magnitude diagram that displays a theoretical stellar population of one single age and metallicity. So in this example here, you can see the upper color magnitude diagram, and the green curves are 3.5 gigayears old, more or less, and the red ones are around 5 gigayears old. And here you cannot see it very well, but the solid circles, so in each color, the leftmost isochrons are low metallicity, and the rightmost are high metallicity. So you can see here, we can start seeing a problem, which is we want to use the isochrons to see how, so what's the relative contribution of each theoretical populations to the dataset, right? Meaning, for example, if we take this star, we can say, well, maybe it's the metallicity of this isochron, but there's a problem, which is that the color magnitude diagram is degenerate in the bright part. Why? You can see for these stars here that you can imagine these red older isochrons as being a metallicity range, and same for the green ones. So you can see that these 2 ranges of age and metallicity overlap in this region, meaning essentially that we don't know if these stars are younger and more metallic or older and less metallic. And this is what we are going to try to show. So what we realized is that this degeneracy does not exist in the center region of the color magnitude diagram. In this plot, in the upper right panel, you can see 3 different grids of isochrons. The red ones are 1 gigayear old, and then blue is 5 gigayears, and green is 10 gigayears old. And they have different metallicities. So what happens is that when you look at this lower part, the isochrones of the same metallicity but different ages almost overlap with each other. Meaning that if there's a star in the dataset that is over here, we can most certainly say that it has this metallicity and not this one or this one. There's no overlapping here. And this is how we are going to try to break this degeneracy by looking at the lower part. In this figure, you can see, this is sort of a spoiler, but you can see what the metallicity distribution of the dataset is fitting with these three different isochrone grids of different ages. And the distribution is almost the same. And notably, we are getting more or less solar metallicity, unlike the GALAR 2024 study, which is subsolar, and we would expect solar metallicity in the solar vicinity, right? So this is why we are doing what we're doing. Now I'm going to talk about the method. So we are using parsec isochrons. So we are downloading them from there. We are using a Krupa initial mass function. And we also have to resample the isochrons because we have very few points and we want these nice lines. So yeah, we have done it so that the consecutive isochron points are less separated than 0.001 magnitudes to have a good sampling. We also have decided, so why did I mention the previous slide? Because we are going to split the study in two. We are going to look at the lower end, the fainter end of the color magnitude diagram to get metallicity. And when we get this information, we are going to use it to try to infer age and break this degeneracy in the upper part. How we are going to do it? Well, we're going to follow a maximum likelihood approach, which basically will give us what relative weight each isochron has on the dataset. Of course, as within every method, we have to test it. We have chosen to test it with mock catalogs, which are basically fictitious stellar population, fictitious datasets that we know the age and metallicity distributions of, to see if we can, with our isochron retrieve the same age and metallicity distributions. We have used, since we are going to split the analysis, we have used one simulated catalog of one single age and several metallicities in the lower part. In the upper part, we have the opposite. We have one single metallicity, which has chosen to be solar, because as you will see, that's what we get, and several ages. And then we are going to go to the upper part and use this degenerate grid of several ages and several metallicities to try to see if we can get the distribution of both age and metallicity at the same time. It's worth noting that we also have selected more or less the same amount of points as there are in Gaia for each state. So what is it that we're getting? Well, this one I didn't mention, but if we feed our model with single stellar populations of one single age and metallicity, we applying the isochron rates even if they are different age. So this is for different metallicities 1 gigayear of data points, and if we apply even the 10 gigayear grid, we retrieve the distribution fairly well. And then for the data sets I mentioned before, here we have a normally distributed metallicity, which is the data set you see in black, and we are retrieving almost exactly the same curve, barring some minor discrepancies. So here it works quite well. And then for the age, what we have done is we have taken an entire sample in the color magnitude diagram of solar metallicity and then a uniform star formation rate, right? This is what this green line here is reflecting. The problem is, because we are analyzing only the upper part, we are cutting in magnitude and we are sort of introducing a bias in the mock dataset towards younger stellar ages. And this is the blue line here, meaning when we fit our model in the upper CMD, we have to retrieve this blue line. And we see that the distribution is quite spiky at younger ages, but we can recover more or less the general trend in the star formation rate when we use one metallicity and different ages in the upper part of the color magnitude diagram. But we also have data sets that are age metallicity degenerate. So we have tested for a data set of 3 different metallicities and more or less a constant metallicity distribution and also a constant star formation rate. But since, as I said before, we're fitting in the upper CMD, Then the data set, which is what you're seeing in red, by the way, I'm sorry. Here, I didn't explain it right. So here you can see in the leftmost panel, it's the cumulative metallicity distribution, and in the rightmost panel is the cumulative star formation history. In red, we have the mock catalog, and then in gray, we have what we recover with our isochrone rate. So this is more or less uniform, and we recover more or less uniform metallicity, except for some spurious peaks at the extreme values. And here for H, as I said before, the mock catalog is has a little bit of a slope, even though it is constant, and we recover more or less the same thing. Notably, there's a spurious peak at all the ranges, so we will have to account for this when we analyze it. So as promised, we now go on to analyze the dataset, and what we get is in the lower part, using our metallicity grid of one single H of 1 gigayear, because as I mentioned before, this doesn't really matter in this part, we get this distribution. So you can see it is fairly normally distributed. These peaks right here can be explained more or less by what we saw before. There are some spurious peaks even with the dataset. And then there's this huge spike at our highest metallicity value. We are getting this spike when we analyze with 1H and different metallicities. Even if we increase the metallicity range, we still get it at the most metallic value. And this probably has to do with unresolved binary stars. And we are currently working on correcting this, but yeah, we can ignore it. And the good news is that we are getting normal distribution around solar metallicity, which is good. It's what we expect. And then we analyze the data set in the upper part for one single solar metallicity, which is what we got before, and different ranges. And what we see is that there's very low star formation history at all the ages. Then there's this spike at more or less 4.5 gigayears ago. And then at more or less 3.5 gigayears ago, the star formation rate goes up and it's sustainably higher. And then there's a lot of noise, which, as I said before, we have this noise, but we probably can recover a general trend. Then we go on to analyze the upper part with an H metallicity degenerate grid. And we are using 36 different H's and 8 metallicities. And what's interesting here is that we are recovering a metallicity distribution that is very similar to what Gallard gets, which is subsolar. The peak is at slightly subsolar metallicity, so around minus 0.1. And then as for the H, we have this peak at all the ranges that we said is probably spurious, and this strange spiky distribution that is not, remember, this is not constant SFR, because that would be a slight slope, a slight positive slope. Yeah, but here we didn't tell the model anything about the metallicity distribution. And since we did the analysis in the lower part, where metallicity distribution is reliable, we can apply this as a prior to this analysis. And this is what you see here. So if we do that for the dataset, what we find, of course, here, this you can ignore it because this has been, the model has been forced to output this. But then the star formation history, barring these spurious old age and young age peaks that appear, is more or less compatible with a constant star formation history, which in the field is from 6 gigayears ago is more or less reasonable. And this is what we are getting. So yeah, in conclusion, what happens is we can recover metallicity fairly well in the lower color magnitude diagram. Because, as we said, the color magnitude diagram is not metallicity degenerate in the faint region. And however, when we apply just one metallicity and different ages, our information is not informative enough at younger ages. But we do recover general trends, and we see this spike at 3.5 gigayears ago, then sustains the formation history. But then when we do this with the isochrone of different ages and metallicities, we get a metallicity without a metallicity prior, we get results similar to Gallard. So nice, because we are doing something extremely similar to what they do. But then when we apply our prior in metallicity, we get star formation history that is compatible with constant star formation rate. So yeah, this would be all. And thank you very much for attending the presentation. And thank you at large for my time here. It's been wonderful.
Questions or comments? Antonio, since you had the question from before, now you have. Hector? Did you use J-VAR?
Thanks for the presentation. It's very nice. Just curious, no? You get in the end when you apply the prior, you get slope, and you interpret it like this is like a solar constant star formation rate. I assume that the slope is compatible with the slope that you get when you use the MOB data. I mean that the amount of.
So this slope, yeah, if you look at the MOB data,
Quantitatively, I mean.
it is fairly similar. It's similar to both the MOB data and the recovered star formation history. Yeah, there are some peaks. So what it is compatible mainly because our recovery of a constant star formation history is not that great, right? So here you can see that there are sort of spikes. So yeah, it is compatible, but a lot of things would be compatible. But it is compatible, and this is even in this region. This is even nicer than what we have for the MOB data. So, long story short, it is compatible.
So you measure the metallicity distribution in the faint stars, the lower luminosity stars, and then apply as a prior to the higher luminosity. What happens if the IMF depends on the metallicity?
If the IMF depends, yeah. So we are assuming that, yeah, since we have most of the mass, so most of the stars are in the lower region. Yeah, we didn't include this analysis because we are assuming for our grid always a group initial mass function and constant initial mass function. I am not aware, I don't know if my supervisors are, but I'm not aware if the initial mass function in the solar vicinity should be metallicity dependent. Maybe you can answer that. So yeah, we didn't do that. We just assumed.
We can be.
Yeah, as far as I know, absolutely no one have tried a variable initial mass function with metallicity in this kind of studies. But yeah, in principle, for stellar clusters, stellar structures, nearby the sun, Krupa is the one that is used, always fits, always works. And that's it. But that's a good tool.
If it ain't broken, don't fix
it. Exactly.
I do have one. At some point when you said that, at some point you said, now we have metallicity which is compatible with zero because it's the solar neighborhood, so we expect it. And then you go like, but then at the end our result is metallicity minus 0.1.
So you want me to comment on that?
Yeah.
Sure.
So you really had me there. I was like, okay, so he managed to reconcile.
Yeah, sure. So this minus 0.1, 0.2 metallicity is what happens when we don't apply a metallicity prior. So here we are basically doing a very, very similar thing to Gallard. And it is encouraging that we are getting similar results. So if we go back to the metallicity distribution, theirs is slightly subsolar. And without the metallicity prior, maybe I wasn't clear enough in the end. I was nervous because I thought I didn't have much time. Without metallicity prior, we get subsolar. But we believe that this measurement in the fainter color magnitude diagram is much more robust. This metallicity measurement, at least, is much more robust than the other one because there are a lot more data points and there's no degeneracy with age.
And just going back to Hector's comment on the trend of the age, and you also commented there's a few spikes there. Can it be related with the fact that at the end of the day the nearby stars is a small catalog, it's only 300,000 stars. Can that be just a scatter due to the fact that you're making lots of bins out of only 300,000 stars?
So it could be
And
a lot of
actually,
things.
and you're removing half of them.
It could be a lot of things. It could be this. We are currently working with a data set of 200,000 points, but mostly we believe that this is due to the binning in the choice of the isochrone rate. I forgot to mention, and this is important, that in this mock analysis, we were having some trouble with retrieving the star formation history, and we were getting things that were very similar to this. So very noisy at young ages. But what especially highlighted was, he said, okay, when this red distribution that you see is the mock data, but this nice, more or less constantly increasing distribution only happens when you choose the right binning phase, or the right bin. If you don't choose it, it goes spiking. And what we did was we selected the grid to fit those bins of the mock distribution that give us a nice slope. So currently, this is still work in progress, but currently we believe that this is mainly binning, but it could be a lot of things. Like as far as we know, it could be real results, probably not. But yeah, and data set is also fairly small, so it could be that as well.
Just a comment. It's interesting that the marginal distribution looks similar or regards you the constant star formation rate. However, when you see the distribution of the dimensions, you see that there is no uniform age metallicity relation. So all that conclusion is only for the marginal age distribution. You can see even some different episodes at different metallicities. So,
that is right. I also forgot to mention this. We can even see a correlation in age and metallicity, which is as expected. So older are less metallic, younger are more metallic.
Yeah. And this is extremely important because one of the first motivations to do all this work is that if you go back to the star formation history presented by Gaia,
yeah, this one, right?
That one. Look at that mess. I mean, that could be real, but I find no plausible physical explanation for that. You would expect, as Sergio said, older stars to be more metal poor and then to have some sort of chemical enrichment, right? But what they detect is like this inverted age metallicity relation. And this is more or less the same that we were getting without using the prior. Once you put the prior and then play a little bit with the binning, then you get something that resembles more what you would expect.
I was gonna say, but how much of this expected correlation is already included in the isochrone?
The isochrones are
Yep.
So the isochrone, sorry.
They're theoretical, but what I mean is maybe a theoretical model already assumes this relationship between age and metallicity.
And let's
So when you recover
that,
with the isochrones.
Well,
I know the answer.
should I answer first? Or?
Yeah, no, you answer.
So
it's your call.
What I would say to that is when you look at the mock data, you don't really get this in the metallicity, in the free metallicity beams that can be considered not spurious, right? You get stuff that is more or less fairly constant, and also the grid. The grid is just square grid in age and metallicity. So I would like to say that the grid is not biased towards this, and mock data also suggests minimal bias. I don't know if this is Andres' answer.
Yes, exactly. So when you choose the isochrones, what you do normally is that you choose an uniform grid in age and in metallicity. So you will have examples of very young stellar populations that are also metal poor, and the opposite as well, right? So then the algorithm chooses the best fitting isochrones, and the fact that you see a relation that follows the logical trend is telling you that it's doing something reasonable. But in principle, the model could choose, whatever over that regular.
Is this how it works?
There's still some of the trend is visible. There is not as pronounced, but the -0.2 metallicity is very young, and the 0.4 metallicity, I mean, very old.
Yeah, but those peaks are outside the.
Outside the model, yeah.
Yes, those are outside the model. I don't know why this is happening.
Is, degeneracy effect. Yeah, that is the point of these tests, to see when where the model is failing, and it's failing this kind of way, and it has a trend, like a positive slope. That means that the older population are less metallic, and the younger are more metallic. So the point is of this test is show that the degeneracy always exists, and we must be always functional.
Yeah, so to that I would add that these Fourier's metallicity peaks are biased towards an age metallicity correlation, but the age metallicity degeneracy, as Jairo mentioned in the color magnitude diagram, also would suggest this, because these points over here would be most likely fitted by young metal poor isochrones, and the ones at the rightmost will be old metal grids. I mean, sorry.
Whatever.
Antonio?
Yeah, can you go back to the age metallicity relation of Carvajal?
Yes. The good one.
The good one. So, I trust your results because I think your method is more sound than the one they used. But to be fair, I think this relation and also any other relation can be explained if you involve the right amount of infalling gas and the right metallicity and so on.
Migration.
And migration. So
Also,
bullshit.
There are too many free parameters.
yeah, it's been discussed that this might be also merger with Sagittarius and passage by what's this called? Jairo, help me. The
Magellanic Cloud.
well, when the Sagittarius cloud passes by the very center, something like that. It's also been argued that this expression could be that. But yeah, there are a lot of free parameters. Long story short, we don't really know.
More data is needed.
But that would imply that you have a significant amount of stars around 10 gigayears with solar effects. Do you see that around the universe?
Like, in order to invoke radial migration, you would need heavily biased
Yes,
radial migration.
Radial migration. So that's the thing. Like, this could be, I'm not saying that this is wrong, but what I'm saying is that it's not what
you need to fine tune.
Yes, you need to fine tune lots of parameters to get that. In their paper, they also compared to other spectroscopy surveys. They use Bayesian methods to assign ages to the stars, and they claim that using this other data, you also see this trend. But I don't quite agree with that, because when you see the plots, they are not the same. I don't know. I just find that suspicious.
Another point, the solution, we demonstrate that if the solution is affected by age metallicity degeneracy, we are getting a subsolar solution. They are getting a subsolar. So possibility here is that this solution is affected also by humans.
If we have no more questions or comments, also because we have quite a little bit of time, there's three things I'd like to mention. The first one is, I think we should give a round of applause to the supervisors of the summer. At the wrong moment. I think we should give a round of applause to the summer students. And I understand that the summer students are going to organize some sort of farewell party, so expect something to be organized by then.